Hi Rockridge, this is Mrs. Berger, and today we're going to be talking about curves of best fit. So let's get into what we mean by curves of best fit. So our first page of our notes is here. So when we're collecting and analyzing data, we're given discrete data points. So data points about something that happened already in the past. Somebody collected some individual discrete data points. And typically we put those on a scatter plot to see what they look like, see what the shape of them is. And once we put those discrete data points on a scatter plot, oftentimes we're asked to find a model to fit that data. We're supposed to fit a model to that data so we can assess the past and predict the future. So that's the whole point. We've got some data points. If things continue as they are, what's it going to look like in the future? Or what can we say about what happened in the past? We need to fit a model to those actual real-life data points. So for every scenario, the behavior of the data is different, and we need to have tools to help us decide a good model so that we can assess the past and predict the future. The first tool we have is the statistics capabilities of our calculator. So we're going to be doing a lot of calculator work today, a lot of button pushing, so make sure you have your calculator right there with you. And the first thing we should do when we're looking at these statistics and fitting curves of best fit is make sure two things are set on. Make sure stat diagnostics is on, and we do that by pushing the mode button, going to stat diagnostics, and making sure that it's on, and then second quit. And then go make sure stat plot is on. So we go second stat plot, that's on the y equals button, plot 1 or any of the plots, and turn them on, and then second quit. So I'll show you what that looks like on my calculator here. So I'm going to go to the mode button and scroll down to stat diagnostics and make sure that that is turned on. If it's off, I'm going to go over here to my cursor right here and make sure that I enter when it's on. Once you hit enter on the on, second quit, and then go second y equals or stat plot, and make sure at least this first plot 1 is on. If you want to go ahead and just turn all plots on, that's fine too. For number 1, if you want to do just one, you hit 1, and then make sure your cursor is over the on and hit enter, and therefore stat plots is on, and you can second quit. You can leave those on for the rest of this unit. It shouldn't have any impact on your other work. So that's what we need to make sure that all the data comes up as needed. So that's before you start. Now, we're going to enter the data. We're going to have 3 different examples that we look at today. And when we enter the data, we're going to go to stat, the button stat, edit, and then you're going to enter your values in list 1 and list 2. I'll show you where that is. So if we go to the button stat, edit, we'll enter a bunch of data in list 1 and some corresponding data in list 2. You must have a 1-for-1, so if you have more data in one column than the other, our work here is not going to work, so make sure that you've entered your data correctly. This is actually the data for our first problem today. So once we enter the data, and again that was stat, edit, and then enter your data in here, then we take a look at the data. To view the data, to see what that scatter plot of the data looks like, we go zoom 9. So if I wanted to look at this data, I would say zoom, and then zoom stat, or zoom 9. And this will structure our window so that we're only looking at our data that we input in the stat edit. So we can look at the shape of our data, okay? And that's really important because we need to make some suggestions about the model that we're going to fit to this data. Does it look like a line? Does it look like a parabola or a quadratic? Is the data growing or decaying exponentially? We need to look at this data instead of just looking at it in a table. We want to look at it on a scatter plot, and we do that by going zoom 9. Now, once we look at it, we're going to choose and calculate a regression model, and we do that by going back to our stat button. We scroll over to calc, and we pick a model. So let me show you what that looks like on the calculator. We go stat, scroll over to calc, and we pick one of these models. Model number 4 is a linear regression. Model number 5 is quadratic regression. Model number 6 is a cubic. Model number 7 is a quartic. This is a linear that we use in statistics class. We can skip this one for now. This is natural log, and then choice 0 is our exponential. So those are all the different models our calculator can help us fit to our data. So we'll pick one of those. When we pick one of those, and I'm just going to pick linear for now, just to do something. If you looked at your data that you put into your calculator just for funsies, and you saw a different curve, go ahead and pick a different curve. For this point, it doesn't really matter. I'm just going to pick linear. So I'm going to try to fit a line to that data, and I'm going to hit enter. My x values are in list 1, my y values are in list 2, so I'll go ahead and enter all the way through this. What this is telling me is the best fit is this line y equals ax plus b when a is this number and b is this number. Okay, so that's how we fit a model to our data. The calculator does all the work for us. Once we determine what kind of model we think would be good, we make the calculator determine what the actual y equals equation is going to be. Okay, so those are the statistics capabilities of our calculator. That's the main tool that we're using, along with a couple of other things. So you may have seen, as we move down to the next section, you may have seen an R2 or an R squared in our output. You should have seen it. R squared is this number right here for this model. R squared is the coefficient of determination. This is our tool number 2 that we're going to use. Coefficient of determination is called R squared. It tells us how much of the variation in the variable is accounted for by the regression model. So we always have an R squared between 0 and 1. It's never negative, it's never more than 1. It's always something between 0 and 1. So it could be 0.2, 0.3, 0.4, 0.4579, 0.998, anything between 0 and 1. If R squared equals 1 exactly, then that means 100% of the variability in the response variable is accounted for in the model. So it's a really, really good model. It's a perfectly modeled model for the data that we have. The model, the line we drew, or the curve we drew, fits the data, goes straight through the data perfectly. If the R squared value that spits out is closer to 0, let's say 0.2 or 0.3, we have not done a good job of fitting a model to our data. It's really probably not a good way to predict the future or assess the past. So we're really trying to find a model that has a really nice, pretty R squared, a nice R squared that is close to 1, 0.9, 0.98, maybe like a high 0.8 number, but definitely not a 0.2 or 0.3. I would ditch any model that came out with a 0.2 or 0.3 for R squared. That's just not a good fit. And again, we found that when we ran our regression model, when we did the stat calc, and we picked a regression model, and we hit enter, 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 and at the bottom of that list was an R squared value. That's our coefficient of determination. So again, for us, here's what I found here for mine. Now in this class, we're not going to be addressing R. We'll talk more about that in statistics if you take that class. But R squared is what we'll use for our coefficient of determination. So that's our tool number 2. Tool number 3, quite frankly, is our common sense about the scenario. Okay, so definitely as you're looking at these different models, if you've got a model, one model that tells you an R squared of 0.9 and another model that tells you an R squared of 0.91, those are so close and they're both very good fits. How do we pick which one's the best one? Well, that's when our common sense comes into the mix. So for instance, if we were looking at data that talked about the sales of rotary phones, rotary telephones, those old phones with the circles on them, those old phones from 1980 to 2018, you would not expect an upward-facing model, right? You'd expect data that looked something like this, right? It's going down, either linearly, or maybe it's data that goes it's decaying exponentially. From 1980, it probably doesn't look like a parabola, right? It probably didn't grow after 1980. Definitely probably went down, so this wouldn't be a good model. So what I'm saying is the sales of rotary phones would probably be modeled with exponential, negative exponential maybe, or a negative linear, but probably not a quadratic, definitely not a cubic, right? Definitely not a cubic. This thing is, these sales of these phones are not going to go up, or they're not going to go down only to go up and then down again between 1980 and 2018. That's just not going to happen, okay? So again, if you have one model, let's say you've got a negative exponential model that has a 0.9 for an r squared, but you also have a cubic model that's got a 0.91. You would negate the cubic just because we know that these phones are not going to pick back up in sales again between the time. So we're just going to use our common sense. So that's what I mean by using our common sense. Another thing we can look at is things in nature, so the growth of plants or bacteria. So those might be modeled with natural log, or that ln, natural log, or ln. That's a good model for that, definitely. That's why we call it natural log. We might have some kind of exponential growth, positive. And when I say negative or positive, I mean that's the leading coefficient. Negative or positive is leading coefficient. But probably not, so in growth of plants or bacteria, again, probably not cubic, right? These things don't grow. They don't grow, and then go back down, and then start growing again, right? That just probably doesn't happen. Probably not cubic. Probably not quadratic of any sort, right? They don't go down and then go up, right? They don't go down in population and grow up again. So these are not good models. So cubic, quadratic, probably not good models just based on our common sense, right? Those are probably not good models. But natural log, exponential growth, those are all good models. Now, hopefully you've seen several of these in the past, but a ball or projectile, if it's kicked or thrown or shot in the air, you know what that looks like, right? It goes up and then it goes down again, okay? It's going to be modeled with a quadratic, and it's going to be a negative leading coefficient quadratic, right? A negative quadratic. And it's not going to be modeled with anything else, right? Unless you're on a different planet with different types of gravity, it's not going to be modeled with anything else. So even if you've got a really great fit, a great r squared for a ball that's been kicked in the air that is associated with a cubic or an exponential, even if that r squared is really great with that exponential model, you should pick the quadratic because that's how those projectiles and those balls behave in real life based on your common sense, okay? All right, so now that we've got those three tools in mind, let's take a look and make sure that you can recognize all the different types. So take a moment, go ahead and pause the video, and just think to yourself, if you were to enter data into your calculator and then you hit zoom 9 to look at the scatter plots, which model would you pick if this was the data that you saw? So take a moment, pause the video, and jot down the model that you think these are, and then play the video again to see what the answers are. Okay, hopefully you took a moment to take a look at that. Let's look at the first one. So the first one, you should have chosen logarithmic. And that was a horrible drawing, sorry about that, I don't have my pen. But this data is looking logarithmic. And so the model that you would pick, so this is logarithmic, and you would pick a y equals ln x, okay? That's the one you would pick for that one. For the second one, you probably knew this one immediately. It's got two curves, so it's what? It is a cubic. So this is a cubic, and you would pick the y equals ax to the third plus plus bx squared plus cx plus d. That's the model that comes out of cubic regression, cubic reg. So that's the one that if you see that on a zoom 9, you should pick this model. If you see this in your zoom 9, you should pick exponential. This is exponential growth. This is exponential growth. You should pick regression, exponential regression. And you're going to see a spit out from the calculator of y equals, oops, sorry about that, of y equals a times b to the x power. And we'll see that today. If you see this, it is also exponential, but instead of growth, it's decaying. So this one is exponential decay. Again, you're going to choose the exponential regression choice. I believe it's choice 0. And it's going to be the same output, but your a is going to be a negative number. I'm just going to make that little note to ourselves. Your a is going to end up being a negative number times b to the x power. Okay, that's the model your calculator is going to give you for that. And then this one, of course, is a quadratic, and so you'd pick quadreg for that one. Quadratic, you'll pick quadreg, and of course will output y equals ax squared plus bx plus c. And again, any of these letters A, B, C's, A's and B's, those will all be provided to you by the calculator. The calculator will spit out what those A's need to be, so you just need to plug those in. We usually ask you to round to 3 decimal places, okay? Oh, and come to think about it, this logarithmic probably has an A in front of it, most likely. Okay. So make sure that you can recognize these. If you do a Zoom 9, you can recognize, oh, I'm going to need to pick a cubic reg for that, obviously. Okay? All right. Let's move to our first example. We're going to go easy. We're going to go back to line of best fit. You probably did this in earlier grades when you were given data and you had to fit a line to that data. So we're going to just try out our calculator capabilities. So this is a bunch of data that anthropologists use. If they dig up a bone, a leg bone, a femur bone, they can go back and say, all right, the person who owned this bone was this tall, was this height in centimeters, okay? So the input is the femur length, and the output is the height of the person, okay? So x and y. And I would highly recommend that you label your data like this so that you know what your equation actually means by the time you get it back, okay? All right, so go ahead and again, pause the video and enter this data into list 1 and list 2. Do it carefully, make sure you have a 1 for 1 every time, and then we'll run our linear regression together. So go ahead and pause the video and enter that data in the calculator. All right, hopefully you've had some time to do that. So you hit Stat, Edit, and you entered all this data into list 1 and list 2. And then, since we led the witness here, we told you that we needed to do a linear regression. You should have gone to Stat, Calc, and choose Linear Regression. Now, first of all, if we didn't tell you it was linear regression, you would have done a Zoom 9 and seen that this data looks pretty darn linear, right? It looks like a line would be the best fit here. I guess you could argue some other couple of examples, but this one right here looks like a line. So we'll go ahead and say Stat, Calc, Linear Regression, choice 4. And when we hit enter, 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 our calculator is telling us that the best fit is y equals 1.923x plus 80.681, and we have a great R squared of 0.93. So we can go ahead and fill that in. I'm going to do that now. Okay, so I jotted down that equation, y equals 1.923x plus 80.681. So this is going to be the ruling equation for this scenario. If we need to look at any femur length, we can predict what the height of that person is. Our coefficient of determination is 0.933. So I would declare that this is a good fit, right? This is a good fit. That's a good R squared. So I feel pretty confident about that, and the data looked linear, and this all makes sense, right? The longer your leg bone, the taller you are. That common sense makes sense. Now let's figure out if we can take a look at these things. So an anthropologist finds a femur of length 58 centimeters. So he found an X, right? He found some kind of input, and he's going to be calculating how tall that person was. So what you'll do for that is you'll input 58 centimeters, 58, in here for X, and then solve for Y. So you'll input 58 for X and solve for Y. So go ahead and try that. And hopefully after you calculated that, you found that the person was 192.2 centimeters tall. Okay, so that's just inputting that. Now let's look at a different problem. If someone is 151 centimeters tall, what does our model predict for their femur length? Now that doesn't necessarily mean their leg is this long, but that's what our model predicts. So if you have 151 centimeter tall person, that means you are given the y value, right? You have the y value, and you're trying to back into the x value. So you'll take this 151 centimeters and replace y with it, and then you'll solve for x. You subtract 80.681 from both sides and then divide by 1.923, okay? So go ahead and try that. If you need to, pause the video. And hopefully you got 36.57 centimeters, okay? So we'll be doing this for all different types of models. We probably won't have lines from now on. That was just to get us started. But we're going to put data in the calculator, do a zoom 9, run the regression, and see what we can see about a model that fits this data. So let's look at our next example. So this model talks about the speed of your car versus the fuel efficiency. So the miles per hour you're going, determining how many miles per gallon you're getting, these various speeds. So what we'll do is we'll enter this data again into our calculator, list 1 and list 2. Be careful when you're typing everything in, make sure that all the data is correct, make sure you actually typed 55 instead of just 5. But enter all this data in your calculator, take a moment. Again, if you want to remember how you got there, you go Stat, Edit, and enter the data into list 1 and list 2 just like you see here. Pause the video if you need to. But once you have that finished, we're going to go ahead and do a zoom 9. And this data looks pretty parabolic, doesn't it? It looks like a parabola. There might be a little misbehaving data point here. But for the most part, I would say that this data looks parabolic, looks quadratic to me. So I'm going to run a quadratic. I really can't think of any other model that I would go with this. I'm going to go, and it makes sense, right? The faster I go, the better fuel efficiency I get, but it can't go on forever, right? When I get past a certain speed, my fuel efficiency goes down just because I am using so much energy, right? So I'm going to go Stat, Calc, and this time I'm going to pick quadratic regression, number 5. My data is in list 1, list 2, enter, 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 and all of this will work out. And here's what my calculator is telling me the model is. Y equals negative 0.017 x squared plus 1.90x minus 24.833, and that's my equation. That's my quadratic. And it's telling me an r squared of 0.92, which is quite good. So I'm going to log all of this. This is a good model. I'm good with this model. It matches my understanding of the problem, my common sense. It's got a great r squared. I'm going to use this as my model. So go ahead and record that information for us, and then we'll look for the next question. Okay, hopefully you've had a chance to fill in the problems here. So the shape of our curve was a parabola, a quadratic. The equation the calculator told us was this one here. We rounded to 3 decimal places for each value. Our coefficient of determination, or our r squared, is 0.92, which is a good fit. Now, using our model, we're being asked to say, what is the fuel efficiency if you travel 63 miles per hour? So again, 63 miles per hour, that's an input. That's an x value, right? This x value goes along with speed, and a y value goes along with fuel efficiency. So in our equation, x is speed, y is fuel efficiency. So if you're going 63 miles per hour, you'll need to replace every x with 63. 63 squared goes here, times this, plus 1.902 times 63 minus 24.833. So go ahead and calculate the fuel efficiency in miles per gallon given our model here that we figured out. Hopefully you got approximately 28 miles per gallon, give or take. When you do your rounding, it'll affect your answer, but as long as you got around 28 miles per gallon, you're on the right track. Make sure that you use your PEMDAS for these, right? So approximately 28 miles per gallon using our model. Now we're not saying that 63 miles per hour itself is absolutely 100% going to be 28 miles per gallon, because remember, this isn't a perfect fit. However, this is the best model we've got to work with, and so if someone asked you this question, this is the best you can get, okay? All right, let's look at one more example. This is a scooter store sales numbers. So it opened, and in the first year it sold 15, and the second year it sold 23, so on and so forth. So go ahead and enter this data in your calculator. Pause the video if you need to. Enter the data in your calculator, and we'll move from there. When you're entering this data in your calculator, if you need to clear the data instead of overwriting it, when you do stat edit, if you need to clear the whole column, go to the top, hit clear, enter. Go to the top of the next column, hit clear, enter, just in case you need that instead of overwriting the data. Okay, by now you've paused the video and you've entered the data, and so now we're going to look at what this looks like on the scatter plot. So we do a zoom 9 to see a scatter plot of our data. Now this is interesting, it's curving up. We don't see any history of it being any higher over here, so I wouldn't say a parabola matches this. It could be linear, but this guy's sales are going up, and of course if we want to be optimistic, we're going to say they're going up a little better than linearly. It looks like they're going up exponentially, right? They look like they're growing pretty quickly. They were a little bit, and then they're jumping quite a bit. So let's run an exponential regression, because I think this matches an exponential growth, and certainly the person selling scooters hopes it's growing exponentially as well. So we'll do a stat calc exponential reg and see what that does. An exponential regression is choice 0. And we will enter. And let's see what the r squared is here. 0.988. That's a great r squared. And notice what the format of the calculator is telling us. So let's translate what the calculator is telling us into our problem here. So go ahead and pause the video and jot this down. Okay, so hopefully you've had a moment to record down that data onto your paper. So you should have said that the shape of the curve looks like an exponential growth. The equation modeling this is y equals 11.392 times 1.451 to the x power, exponential growth. And we have a coefficient of determination of 0.988, which is a great fit. So we love that model. This sales looks like it's going off to an exponentially great start. Now, how many scooters will they probably sell in year 11 if this continues? So year 11, year is x. They told us that at the beginning of the problem. Year is x. So year 11, you'll take 11 and input it as the power here. So you'll take, remember PEMDAS, E comes before M, so 1.451 to the 11th power times 11.392. And that will give you, by the time you're done computing, go ahead and pause if you need to. Go ahead and compute that out, but that should get you around 684 scooters. Okay, so that's their prediction. If someone, if their bank needed to know what their prediction was for how many they're going to sell, they would tell the bank, we're going to have 684 scooters, you've invested in a great business. Now, the next question is a little trickier, especially because we haven't had our log lesson yet. But if we're asked to estimate the year in which they'll sell 300 scooters, that means, of course, that 300 scooters is their y, so you know that y is 300. And you need to back into what power of x will get you 300. Now, before we learn the algebra, that comes next class, before we learn the algebra, let me show you a little trick on the calculator that we can use. When we run this regression equation, stat calc choice 0 exponential reg, before you hit the calculate button, get your cursor down to store regression equation. And what this is going to do, we're going to take you through a couple steps here where we store the regression equation. So instead of you jotting it down, the calculator is going to enter that equation, y equals, into y equals up here, and usually where we type our graphing. So we're going to tell it to do that by hitting the vars button, toggle to y vars, choose function. And y1 is as good as any. We'll put it into y1. If you need to redo that, rewind the video, pause it, and jot down some notes. But by the time we're done with vars, y vars, and entering it into the function y1, you should see y1 pop up here. And we're basically telling it, please, when you run this regression equation, we like it so much we want to save it in y1. Hit enter, and calculate. The same output will be shown here, just as we were expecting. But also, y equals 11.392 times 1.45 to the x is now stored in, check it out, y equals. To many more decimal places, obviously. So the calculator stored it here, but also the great, wonderful thing, well, we could also do a zoom 9 and take a look. It's now graphed the data and the function, so you can visually see how it fits. But the most fantastic thing about this is, if you go to second table, it's showing you all the different values along that curve, that continuous curve. So if you want to look at, which year were we looking at again? The year they're selling 300 scooters. The year they're selling approximately 300 scooters is somewhere between year 8 and year 9. Somewhere in year 8, they're going to sell 300 scooters. Year 2, they're selling approximately 23, according to this model. According to this model, they're going to sell approximately 300 scooters in year 8. And there you go, around year 8. So again, if you need to pause the video and jot down the notes for how to store your regression equation, that's just a little trick that makes it easier instead of having to solve the algebra. We'll learn the algebra in the next lesson. All right? Go ahead and try your independent practice and let us know if you have any questions.